Thanks,
Yes.
thanks for the invitation. It's a pleasure to be here, and even at this early time. And I'm going to talk about work that I've been doing in the past 5 years or so, where I focused on basically applications of computational argumentation as we understand it to explanation, and in general, and explainable AI in particular. So I'm going to give you an overview of the kinds of computational argumentation that we use in this context, and an introduction, a very brief introduction to explainable AI. And I am then going to give you a kind of a survey of the kinds of things we do with several colleagues on providing argumentation-based explanations that, as we see, happen to be interactive, and that's different from most of the state-of-the-art. And we do this for a bunch of systems, in particular classifiers, potentially built with using machine learning techniques, recommended systems, and schedulers, amongst other things. So there are other applications we look at, but these three categories is what they mostly focus on within this this talk. So I haven't Sarah and Matthias and Mauro. I have 1 hour. How many minutes you want me to leave for questions?
So 15 minutes. So we thought about 10 minutes about questions then in the end.
Okay, great. Thank you very much. Okay, so let us start. Computational argumentation. So what is it that we mean by that in general? Well, what I believe we mean within kind of computational argumentation is a combination of two things: argumentation frameworks and argumentation semantics and corresponding systems that together exhibit properties. So the frameworks are somewhat abstraction of debates of various types. The semantics are ways to evaluate the debate, and the properties somewhat sanction the goodness of the semantics in the context of where we want to deploy computational argumentation. So the simplest form, as we all know, of computational argumentation is abstract argumentation, where the framework can be seen as graphs. Edges are arguments, and edges are attacks between arguments, which are the nodes. But we have studied also forms of structured argumentation, where arguments have a structure, they have premises and claims, and attacks can be understood in terms of the building blocks of the arguments. In this particular illustration, as in ABBA and to some extent ASPIC, we have that for an argument to attack another, it needs to have as its claim the contrary of an assumption premise in the other. So there are various forms of structured argumentation. ABBA and ASPIC are examples. DELF is another example, and logic-based argumentation is a third. Within this talk, structured argumentation, as we'll see, will really not play a role, whereas abstract argumentation will, as will bipolar argumentation, where we have, in addition to the attack relation between arguments, also a relation of support between arguments, labeled here with a plus. So this is just an overview of the kinds of frameworks that we often consider within computational argumentation. We, of course, consider extensions of these frameworks with preferences, with probabilities, etc. But again, none of these will play an important role today. Today meaning in my talk. So what do we mean with semantics? Well, one of the most widespread forms of semantics is given by extensions, as Dung introduced in his seminar 95 paper. For example, admissible extensions. There are various other types. Overall, they are basically sets of winning arguments, where winning means dialectically. In this particular very simple illustration, the green arguments here and here form an admissible extension where this argument is unattacked and therefore winning, and this argument is defended by this argument and therefore also winning. But we have other forms of semantics in addition to extension-based. For example, we have dialectical semantics that are gradual. So this is a simple illustration, computes the numbers, which are basically the dialectical strength of arguments using an argument, a semantics called DF quad that we have defined with Antonio Drago and Pietro Baroni. This semantics has in this kind of uses arguments with an intrinsic strength they start with. In this particular case, the intrinsic strength is 0.5, and then determines how that intrinsic strength is changed by dialectical relationships of attack and of support. Please note, sometimes I put a minus on top of the single line for attack, sometimes, and the plus on top of the double line for support. Sometimes I don't, as in this case. So this is just an example of one of many semantics that somewhat equate to gradual argumentation. What's important is that with respect to the semantics, we have algorithms and systems, and these are of particular interest for this workshop and for this community. We use this algorithm system to support applications that may require properties of the semantics, for example, existence, uniqueness in the case of extension-based semantics, or in the case of gradual semantics, forms of monotonicity, for example, sanctioning that attacks should decrease strength and support should increase strength. So the gradual semantics needs to be defined in such a way that these monotonicity properties hold of the numbers that it computes. And as I said, different properties may be needed for different applications. Now, there are various ways for solving what I call the argumentation equation that I've just given you. So one could, as it often is the case, start with argumentation framework of some type, have in mind some properties it wants to achieve, and then define or choose a semantics that does the job. So in this particular case, what is being chosen, so the variable that needs instantiating is the semantics. But and this is typically what we do. But in reality, one could solve also the equation by using the framework as the variable and saying, suppose I know what semantics I have in mind. For example, I know the gradual semantics for specific elements of interest in my application, and I have some properties in mind for those values that I know that would make those values an argumentation semantics. But I need to identify the dialectical relationship that make that semantics have the properties. So we will see that this second way to solve the equation is useful in some forms of explainable AI. In those kinds of settings, the semantics is provided by somewhat the system that needs explaining. For example, in the case of recommended systems, we have predictive ratings that the recommended system is computing. And we have predictive ratings over aspects of items and items themselves, for example, products and their features. So we can treat those predictive ratings as an argumentation semantics for the products and their features understood as arguments. What we need to find out is what argumentation framework will make sure that those predictive ratings seen as an argumentation semantics exhibit properties that are dialectically meaningful, such as monotonicity. So we will, as I said, we'll see examples of both ways to solve the argumentation equation. Okay, now let me give you a brief overview of explainable AI. There is, I think I've misspelled explainable AI here big time, but I hope you know what I mean. So there is actually a big hype. There has been for a while now a big hype on explainability in AI. This is from a recent issue of The Economist, saying that AI can do a lot already, but it's it's important that it work alongside humans. But for humans to work alongside AI, they need to understand what is going on, and there is a big push, at least from a legislative viewpoint, towards transparent information and communication by systems and make use of data. The GDPR is one such regulation that somewhat pushes towards transparency. There are guidelines for AI that sanction that in order for this AI to be trustworthy, it needs to be able to explain its decisions in a way that is understandable and adapted to the audience of, to the stakeholders that form the audience of the AI systems, and various countries are actually pushing towards explainable and transparent AI. This is the case definitely for the UK, where the Lord Select Committee on Artificial Intelligence has recently, in the last couple of years, come up with again guidance, and where within again the UK there have been recent consultation with industry as to what explainable AI should be doing. So there is a lot of, if you like, top-down energy within explainable AI, pushing towards AI indeed that can work alongside humans because they can trust it, because they understand it, given that it is explainable. So because of this energy in the area, there is a lot of energy also in academia and industry in providing explainable AI solutions. So what is typically happening is that we have a system, for example, empowered by machine learning, that takes some inputs and computes some outputs. For example, in this simple illustration, that my credit card application has been denied. So the idea is that the system, while also presenting the audience with an output, should accompany the output with an explanation. Now, the audience may include expert developers, so machine learning experts, for example, in this case, or clients of a financial institution that makes this decision or uses the system to support its decision making, or a regulator that wants to make sure that the output is actually fair, for example. And of course, there may be beneficiaries that could be the same as the audience or different, but in any case, there are humans at the receiving end. So what form does this explanation take? Well, there are very many proposals these days. One class of proposals sees explanation as feature attribution. So in this particular illustration, could say the card was denied because the client is credit unworthy despite good salary. So in this form of explanation, features such as credit unworthy and good salary that are responsible for the output are identified, and in some feature attribution kind of settings, their positive or negative influence is also stressed. So this is a class of systems that include LIME and SHAP, you may have heard of, as well as other systems that are less method agnostic, model agnostic, for example, LRP, layer-wise relevant propagation, and other kind of gradient-based methods that are more specific to deep learning-like techniques. There are other classes of explanations, in particular, counterfactual explanations are very popular. So an example in this simple illustrative setting is the following. Had the client had a good credit score, the card would have been granted. So here, the explanation points out to what could have been different so as to change the output that was obtained. So in this case, the also responsible input features are identified, but a change to those input features is also pointed out that would change the output. So this is a very high-level view, just to give you concrete and non-simplified examples. LIME, that already mentioned, is a popular form of feature attribution-based explanatory technique. It is one where, like in this particular case, the input may be a piece of text, and the output may be a prediction, for example, that this text is about atheism or Christianity. So these are the two possible outputs, and the underlying classifier in this case will also present the two possible outcomes with a probability. So saying that atheism is more probable. And what LIME does is identifies bits of the inputs, which are blued here, that are responsible, that are in a sense leading to that prediction probability. So this is pointing out which features of the input, which is in this case are terms in the text, are responsible. So this is just an example from the state of the art. And this is an example of the kind of counterfactual explanation that a recent method for this purpose by Wachter et al. Returns. So this would say, score P, for example, score P could be that atheism is predicted with a probability of 0.58. The score P was returned because variable V had values whatever. If V instead had values whatever and all other variables had remained constant, score P prime would have been returned. So in the context of the previous example, this would be amounting to identifying which words would have to be different in order to get a prediction of Christianity rather than atheism in this setting. So this is by no means an exhaustive overview of the explainable AI area. It is just a taster, if you like, to introduce what we are doing. Overall, I would say that what we are trying to address is with argumentation is what I believe are two important deficiencies, if you like, of standard explainable AI solutions, that they are one way and shallow. The two things are connected, and I'll try to explain in a minute what I mean. The fact that they are one way, it means that they are in a sense returned as outputs themselves that the audience can inspect but not interact with. And the fact that they're shallow means that they are really referring exclusively to the inputs rather than to the inner working of the method that is being explained. So what argumentation allows us to do is to actually provide two-way and potentially deep explanations, and it does so by using what I call argumentative abstractions of the inner workings of the method from which the explanations themselves can be extracted. So here, argumentative abstractions are argumentation frameworks, and they are a step towards constructive explanations rather than explanations themselves. So we in argumentation believe that argumentation frameworks are as clear as they can possibly be, but in reality, when you have different audience at hand, you may need to take from argumentative abstractions bits out that then become part of the explanation. So before we move into some of our proposed solutions, let me tell you what I mean with one-way and shallow explanations. So this is the setting that we have. So suppose as an illustration that our inputs are actually ingredients that we have in our fridge or in the larder, and our outputs are dishes, food that we have cooked. Then a kind of shallow explanation would point out to the ingredients used for making the dish alone. Would be a selection of things we have in the fridge and in the larder that, or we can potentially have, or that exist in a supermarket if we're allowed to buy, that contribute to obtaining that dish. So if we were to go for a very deep explanation, we would have to look at the kind of the biology side of things, so potentially the chemical reactions by various means of cooking, and that's what, in a sense, mirrors, if we are, for example, using deep learning, mirrors what the underlying system really is like. But this is going to be, obscure to most possible members of the audience. What I think should be a deep explanation in this case is actually the recipe as to how the system managed to produce, in a kind of stepwise manner. So to illustrate what I mean with one way versus two ways or interactive explanation, the one way could be still that I'm giving you the ingredients, or I'm dumping on you the full recipe of how to do the, how to carry out, in a sense, the recipe itself. But a genuine two-way or interactive explanation may actually start with the high level, make the sauce and the bechamel, then do whatever, that the user in the audience, the specific stakeholder can then question, so, how do I make the sauce? And could I, boil the meat rather than frying it? So there needs to be an opportunity for interaction with, with the system. So argumentation, I will argue and hopefully show you, is a good medium towards two ways and interactive explanations that can go beyond the state of the art. Okay, so I told you that for this vision to work, we need to be able to extract argumentative abstractions from the systems that we want to explain. So which types of argumentative abstractions are we going to use? I mean, we have seen that there are many types of argumentation frameworks we could choose from. In particular, we can choose abstract argumentation, and we will see that this type of abstraction is helpful for explaining predictions from labeled data and for explaining scheduling solutions to problems. We could use bipolar argumentation frameworks, and in particular, quantified ones. These are bipolar frameworks where arguments come with an intrinsic strength upfront, and we use indeed these forms of argumentation frameworks for recommendations from text and deception detection and fact checking from text. So we use a lot of these types of framework when systems are built around textual data. We need to be creative because especially when we are trying to solve the argumentation equation, having a specific semantics in mind and some properties we want that semantics to have, we may not have existing argumentation frameworks available that we can exploit. So we have been creative. We have defined kind of two support argumentation frameworks for explaining counterfactually predictions by Bayesian classifiers. So these two support argumentation frameworks include two notions, two relations of support, which is critical and potential. Critical indicated with an exclamation mark here, and potential with a star. So the critical support is the one that indicates factors that, if changed, would lead to a different prediction. And that's why this form support is useful for capturing counterfactual explanation. Whereas potential support is indicating things that may lead to a change in some cases, change of classification in some cases, but not always. Finally, we have introduced what we call tripolar argumentation frameworks, including attack support and the third notion of neutralizing relation for capturing some recommended systems that we have defined, which are somewhat competitive with some of the state of the art, while also being explainable argumentatively. So this is just a quick overview of some of the things I will touch upon in the rest of this talk, where I'm overviewing some of this work. Okay, so let's start with one of the most recent proposals in this setting. This is this was just presented at ICAI last week. So we basically use abstract argumentation to support prediction from labeled data using a framework that we call DIA, for data empowered argumentation, which is a generalization of an earlier framework that we called AACBR, abstract argumentation for case-based reasoning, that we presented at the KR and COMA in 2016. So within this setting, we have labeled data. So we have here a data set which consists of just 4 data points for simplicity. These are albums, particularly, and they have features. For example, the first one is a the blues jar. The second one is of the blues jar and got US Platinum Award, etc. And each of these data points is labeled with an outcome, which is the outcome we're interested in predicting for unseen data, which is in the last row. So the outcome is whether the album got UK Platinum or will get UK Platinum or not. We have, as I said, an unseen data point, which is an album of which we know the features, but not the outcome. So this is a standard machine learning setting. You have labeled data and you want to predict the outcome for an unseen and unlabeled data point. For supporting this prediction task, we solve the argumentation equation by using abstract argumentation frameworks, the grounded extension semantics, to achieve a bunch of properties, and in particular tractability, existence, and uniqueness, for which the semantics is particularly suited. So how do we go about doing that? So how do we obtain the abstract argumentation frameworks as argumentative abstractions of the data? This is an example of, this is actually what we would obtain for this particular toy example. You can see that the argumentation framework, which is an abstract one, so all the edges are attacks. The argumentation framework includes data points as arguments. The data points are other existing ones from the data set. These are the ones I'm indicating. They're all rows of this data set. And they also include the unlabeled data point, which is the bottom row here, in addition to what we call the default argument, which is indicating the outcome we would obtain by default if we knew nothing at all about the input. So this is a kind of bias of the system that needs to be given as an input to the framework, as we shall see. So in a nutshell here, arguments are labeled or unlabeled data points or the default argument, and attacks are due to disagreement on the label. So for example, this argument 2m attacks the default argument because the label, the outcome of 2m is not UK Platinum, whereas the default one is UK Platinum. So there is a disagreement on the label that determines this attack. This is true for all relations except for this. This notion of this bit of the attack relation is due to irrelevance, and we can deem this particular data point to be irrelevant to the unlabeled one because it has features, for example, positive reviews, that are irrelevant to the unlabeled one. So I'm trying to give you here the intuition. The attack is arising from disagreement on the label and informativeness, so that more informative arguments attack less informative arguments, where more informative here means with more features and minimally so. And when the argument from the unlabeled data point is considered, then irrelevance is what detects attacks. So we can see that this is an abstract argumentation framework, but we can also see to some extent that the data points have a structure because they have a set of premises, the features, and a claim, which is the outcome. And although we haven't done so, there is built into the system a notion of preferences between arguments that dictates the direction of the attack, which would otherwise be symmetric. And this preference is what gives the informativeness, basically. So we haven't looked at this way, but for you as a community, I can say, because I believe you can probably see what I mean. So once we have obtained these argumentative abstractions of the data, what we do is we make the prediction amounting to basically the presence of the default argument in the grounded extension of the argumentation framework. So in this particular case, we predict for this unlabeled data point that you will not get UK Platinum because the default argument, which is the root of the tree here, does not belong to the grounded extension of this framework. Grounded extension is indicating here, underlined here. So we have the unattacked arguments and the arguments that are defended by unattacked arguments. And given that the default argument does not belong to it, we would make a prediction of non-UK Platinum. Overall, the framework works as follows. When you apply it to more meaningful examples than what I've just given you, you need to have a data set which is sufficiently manageable to be dealt with by the argumentation debate miner that extracts the argumentation framework as an argumentative abstraction of the data. So in order for this to be the case, you need to think creatively about how to extract the characterization of the data point in the previous example, the set of features, so that you go from a possibly very large data set to a manageable data set in terms of size. And similarly, we apply this characterization extraction to the unlabeled data point that may be large to start with and becomes manageable after this process. The extraction of the argumentative abstraction takes 3 inputs in addition to the data set and the labeled data point. This is a partial order over the characterizations, basically. The default argument, which is a characterization which is kind of minimally, in a sense, leading us to determine the default outcome, and the notion of irrelevance between labeled data points and the data points in the data set. So we define formally what arguments and attacks are drawn from all these inputs, and we obtain an argumentation framework from which we make predictions, as I have just illustrated, by looking at membership in the grounded extension of the default argument. But we can also build explanations, which in this particular line of work can be seen as disputes between a proponent and an opponent. And for obtaining these disputes, we use dispute trees from computational argumentation as well. Before I tell you about the explainer, let me tell you that we looked at a bunch of instances of this vision, in a sense, different types of inputs here, different characterization extractions, and different hyperparameters, the partial order, the default argument, and the notion of irrelevance. And we compared their accuracy and other measure, precision, recall, etc., with respect to predictions made by standard transparent methodologies in machine learning, for example, decision trees and k-nearest neighbor, obtaining competitive performance when reasoning argumentatively using the grounded extension semantics. So this is a very quick overview of 3 sets of experiments we have done. We looked at categorical data, an existing mushroom data set. We chose superset as the partial order and not, superset or equal as irrelevance. And we had to choose particular default outcomes to make things work. But we also looked at labeled images and looked at the Celebi and objects with attributes data sets, where we had to change the default arguments to make things work, but kept the same notion of partial order and irrelevance. Whereas for unstructured data, we looked at text and sentiment analysis with 2 data sets. We had to be really creative with the partial order, taking into account weights computed over the the classifiers, over the data, for example, TF-IDF measures, etc. And we had to make different choices for the other parameters. I mean, I'm putting up this slide without saying too much about it, to just say that in order to prove that our method works, we had to, in a sense, be serious about experimenting with alternatives and show that performances are competitive, and in order to be convincing. Explainability per se, the kind of explanations we can draw, will not alone be a convincing meta-argument about the goodness of this approach. But they are an important aspect of using argumentation, because from the argumentation framework that we extract within this methodology, we can also extract explanations, which, as I said, can be in the form of disputes. So these are between a proponent and an opponent node, and they are basically amounting to trees that are extracted from the argumentation framework. Simple example, suppose this is our abstract argumentation framework, then we may extract 2 dispute trees that are sanctioning that A, in particular, which may be the output we are interested in, is dialectically acceptable. One where the proponent starts playing A, the opponent, which is a fictional player in the disputes, puts forward B and C, which are attacking A, and the proponent needs to defend itself against these two attacks, for example, by choosing D and F, or alternative by choosing E as a single attacker of the two. So in the particular application to the DIA framework of this form of explanations, the proponent would put forward the winning default if the default argument is what belongs to the grounded extension, and the dispute would indicate why that default argument belongs to the grounded extension and is thus leading to the default prediction. So these would be admissible dispute trees. But in the case in which the prediction is not the default, because the default argument does not belong to the grounded extension, we need to define what we call maximal dispute trees, which will not be having, which will have the opponent as a leaf rather than the proponent. Okay, this is based on some work that did in the back in 2015 with the XUE Fund, where in addition to using dispute trees, we also define notions of admissibility that are tailored to explanation. Okay, so this is the first application of argumentation with respect to explainability, and I'm realizing I've got very little time left. I got carried away with this approach. We use abstract argumentation also for explaining why schedules are non-optimal. This is particularly important when schedulers are used in applications, for example, for nurse rostering, because although solutions to schedules are fully transparent to mathematicians, the mathematics may not be as transparent to non-mathematicians. So we have used abstract argumentation as a counterpart for scheduling to explain why modifications to schedules by, say, nurses or administrators are not good solutions. And in this particular case, we use the stable extension semantics for supporting dialectical explanations for the users. Here we obtain explanations as conversations in control natural language guided by templates, which are very simple things to be instantiated on the abstract argumentation framework. I don't have time to go in details. We have a system that we presented today, MAS, built exactly on these. We also, as I said, use quantified Boolean, bipolar argumentation frameworks. I don't have time to look at this in detail. We have a bunch of ways to extract conversational explanations again from this bipolar framework. We use the same quantified bipolar frameworks to make predictions and explain predictions towards veracity of input text in a fact-checking and fake news setting. And similarly to the previous application, we use the DF-pod algorithm here. We also define what are called non-standard abstract argumentation frameworks to support recommender systems, outputs, and explaining them. And we extract argumentation frameworks from the predicted ratings, as you can see here. And we treat every single nodes and features, so items and features, as arguments, and we treat this column as the semantics we're after. So we define the frameworks, which are tripolar in this case, although this example is purely bipolar, but in general we get tripolar frameworks here. We obtain these frameworks so that these relationships here of attack and support satisfy monotonicity kind of properties of the semantics. And as I already mentioned, we define two support argumentation frameworks to capture predictions by Bayesian classifiers that use underpinning Bayesian networks, whereby you have somewhat dependencies between random variables as indicated here. And interestingly, in both the case of Bayesian network classifiers, if they're non-naive, and in the case of recommended systems, we may get deep explanations because the argumentation framework goes further than determining the inferences from the input towards the output. Okay, so the thing I want to conclude with, I mean, this is just an overview of what different things we are doing and what kinds of argumentation framework we're using and what kind of semantics and systems for those semantics we're using. An important consideration to make, as I told you, is that the argumentation frameworks are not the explanations. I've already shown you how you can get disputes out of the argumentation framework, so to serve as explanations that can be interacted with. In general, you may have different forms of explanations extracted from the argumentation frameworks. You can have fact-based explanations, linguistic narratives, tabular explanations, and conversational. I briefly overviewed one such example in the case of recommended systems. We are giving a presentation at KR next week on exactly these different explanation formats in the case of recommended systems, and this slide is taken from the paper. We also conducted, and discussed in the paper, a study with humans as to what forms of interactive explanations are more amenable to user consumption. We have asked, we have tried to measure their perception of transparency and seeing that, the interactive explanations increase this perception of transparency, and somewhat it doesn't really matter which form of interaction users use. So there is different forms of explanation, as soon as they are interactive, may be equally liked by users. Again, we'll present this next week at KR. So in conclusion, I have, I hope, convinced you that a computational argumentation can empower interactive explanation, and they can be, and these explanations can be deep if the underlying method is deep. So of course, if you're using a naive Bayesian classifier, which is shallow, you wouldn't get deep explanations. But if you're using a non-naive Bayesian classifier, then you will. I've shown you that in the experiments I have described, in the instances I've described, we are using computational grounded extension for abstract argumentation and the DF quad algorithms for quantified bipolar argumentation frameworks. We are looking at other instances. So at COMA this week, Emanuele will present joint work with Pietro and Antonio, as well as myself, on deploying this similar vision to explain page rank, and actually use page rank, understand page rank as an argumentation semantics for specific argumentation frameworks, which are again extracted. This is another example where the argumentation equation is solved by choosing the semantics first and then deciding which argumentation frameworks to obtain. We are giving a tutorial next week at KR in which I will go with Antonio on a lot more detail on some of the things I told you today, as well as we will present the paper I mentioned on interactive explanations. There is a lot we need to do still, but I'll leave this for your questions. Thanks a lot for your attention.